So, dear all, it's really a pleasure to be there. We are in presence classroom from telecommunication engineering here at Politecnico of Turin last year, NZEB for master degrees. We also have an external expert, and today we will have our 5th educational event series conference about building monitoring, tracking control logic, and smart solutions. The topic of today focalize and enter inside the use of sensor in buildings on control logic for buildings automation, and we will have in all of the presentation a correlation with true buildings, so demo cases, residential building, offices, and living labs, office living labs. This event is inside a series of events supported by the PRELUDE European project. Okay, we already have this academic year a first event on parametric smart solution for building retrofitted and cost optimal. And in the next semester, we will have 2 scheduled events about ICT data-driven buildings, so smart building, and again coordinated through PRELUDE demo cases. And a second event with also external speaker correlated to climate resilient and bioclimatic effects and aspect under climate changes, in which we also have part of the speaker from the Annex 18 of year. Before starting, just a very short recap of the project. PRELUDE project, which is patient building operation utilizing real-time data for energy dynamic optimizations, is an European supported project, okay, which is working and analyzing advanced innovative solution for low-cost smart building and proactive optimization services. We aim to minimize energy uses, maximize self-consumption and renewable usables, so integrating demand and production. And in the same times, improve thermal comfort condition and visual comfort condition, and in any case, comfort condition in building to maximize, where possible, local free running potential. So natural ventilation, or in any case, ventilated cooling, shading control, and so on. The project concept is based on the development of multi-partner platforms with a centralized middleware-based inclusive solutions and several modular, we can say, sub-platform, or in any case, services that perform specific tasks for weather, energy, comfort, and so on. Among the PRELUDE technology that we are investigating, there is for sure the integration of multiple sensor actuators and solutions inside a sole middleware. There is the support of dynamic free running potential exploitation and the use of a dynamic energy simulation platform managed automatically and remotely. Indoor-outdoor correlation model for fast and simple automation with low local correlated simulation performance. Occupancy profiling, weather radiation prediction model, district heating integration, and different approaches for verification, for optimized and different way energy management. And when you can say, for what it is possible, verify the issue, like also the measurement verification approach, support predictive maintenance, and support in several cases the fact that we want to optimize comfort and energy efficiency in the building with specific, for example, customized graphical user interface for user safe actuation and for integrating automatic actuator where present. Last but not least, clearly the renovation roadmap approach that you also were discussed in the last elements. All of these solutions are tested in different demo cases in Denmark, in Italy, in Switzerland, in Poland, in Greece, and in a very advanced Living Lab solution, which is the energetical Living Lab in Austria. Today, we will see some of the presentations that are correlated to this, or to some of these demo cases in a Living Lab. So, the topic of today is focused on building monitor, which is not so easy like it looks like. Okay, it's not only acquiring sensor and position, but has a lot of issues that we try together with our speaker, which are very, very welcome and thanks for being there today, to support control logic how to support optimization, which are the complexity in monitoring, especially when you can say NZEB nearly zero energy buildings and so on. Include lesson learned by real demo cases, so real living labs, but also cases in which people are living, okay, houses. And also we will support and diffuse some of the initial outline of the PRELUDE buildings. The speakers are recognized as experts. Not all of the speakers come from the PRELUDE project. We also have, it's very welcome, Michele Zinzi for the ENEA, which is the Italian national energy agency, which supports very important, I can say, past experience and lesson learned for a living lab in Italy. So today we will have, after my short presentation, 5 speeches. The first 3, starting with Michele Zinzi for ENEA and going to Tristan de Kerchove for ESTIA. We will have further Martin Frandsen for Aalborg University in Denmark. These 3 will really focus on the issue of smart building monitoring, integrating the technology in real buildings. After, we will have 2 other presentations. One from Enrico Prataviera, also supported by Professor Zarrella, but here is University of Padua in Italy, which supports sensitivity analysis for controlling thermovalves. Okay, so heating set point strategies. And last but not least, there is the very interesting experience of the Energetic Living Lab in Austria, presented by Klanatsky, with long-term results for data-driven predictive control. So what is predictive control? How this will arrive? The first presentation by Michele Zinzi, so we are from the ENEA, Italian National Agency for New Technology and Sustainable Economic Development. It will support and show example taken by a real building, which is an office building, that was transformed into living lab, okay, in which the topic is how we can focus and manage the integration of smart solution in an existing building. Okay, it's not so easy to be solved, like a challenge. And we will see how this is applied to performance gap studies in between what is expected and what is the real monitoring. Now, Michele Zinzi is a researcher at ENEA since 2000, has a lot of interest, is very recognized, especially urban housing studies, okay? For Italy, it's also very famous for energy labeling tools, okay? And things like that. It's also support and is associate editor of the severe journal Energy Buildings, Prime also, and an expert member for the International Energy Agency Energy and Building Community for Italy. It's also included in Giacomo and so on. The second presentation will be by Tristan de Kerchove. We are an ESTIA company, and PFL Campus is a Swiss company, okay, that's focused like experience in building physics and building energy performance optimization in Europe and Switzerland context. Tristan is an engineer working in the company, okay, on the building performance point of view and correlation between what they do and innovation, okay, and research. The presentation will focus on the challenges which is correlated to building monitoring and actuating with special focus to real buildings in the Switzerland context. We have a Swiss case study in the Geneva city, and here the topic is also high energy performance buildings are quite complex to be monitored, okay? Because we're speaking about few amounts of consumption for square meter. The third presentation is by Martin Frandsen. We are from the Aalborg University in Denmark. Okay, it is a research assistant, Department of Built Environment, Aalborg University. Okay, specialized in indoor environmental quality, energy engineering, and so on. This support inside the PRELUDE project the 2 Danish demo cases. One of these will be, I think, used a lot in the presentation. They are very smart building, okay, advanced smart building solution. And here the approach is to show how to monitor NZEB building, lesson learned, for establishing, defining monitoring system and communicate what we monitor to support actuation in single family houses. That's not easy again. How to communicate and how to monitor, again, very efficiency building. After we will have the presentation by Enrico Prataviera, which is here in present. Thank you a lot for that. Okay, and in this case, Enrico Prataviera is a postdoc researcher at University of Padua, has a background as energy engineering, but he's also worked a lot in the integration of code, okay, in the building and energy sector, which is quite difficult, okay? Some of the people are erring is approaching on the telecommunication and informatic point of view, this approach, and you will see the complexity of applying this type of code in a building sector which has its own rules, okay, and backgrounds. Is specialized in HVAC system simulation in urban scales. The presentation will support sensitivity analysis based on HVAC simulation analysis that has like approach, we can control smart valves, okay, you know, the control of set points, okay, in the residential houses with a centralized dating system with the possibility to control each radiator in some way, and how we can manage at better the scheduling, okay, of this radiator, and how scheduling this radiator according to the occupancy, for example, may anticipated or not anticipated the activation of this radiator may support a variation in energy performance. Last but not least, we have Peter Klanatsky from the Burgenland FB Pinkafels. Here we have is a lecture, okay, in the Department of Energy and Environment at University of Applied Science in Burgenland, and also a researcher in the Correlated Center for Building Technology, a portion of Burgenland. He has a lot of experience, if you see, at least 20 years of experience in the field, okay, with the interest of building technology, building automation, and building analytics simulation. In this case, it will support, like it is connected to PRELUDE development and application in the Living Lab of a long-term approaches has been applied for data-driven predictive control in this very, very smart building that they have as Living Lab, in which all aspects are monitored with detail, okay? And so it's also possible to apply a lot of different control logic technology. And here we have really a speech that summarizes the most important outcome from long-term tests. So with different approaches. It's very, very interesting, at least in what I think. So only to remind and leave the floor to Michele Zinzi from ENEA, which is the first speech. This event is inside educational event series of PRELUDE. The task 9.5 will support the involvement of people inside the project or disseminating. We have clearly lecture, conference, and workshop, and this is one of the events in the Blue Lab. Okay, at least 7+ batch final event. And we also support in parallel the inclusion, especially in the past 2 years, of university student groups in developing IoT solution and this type of elements correlated to building to PRELUDE topics. And in parallel, now we are working with large citizen science action that involve regional schools in Piedmont, okay, for indoor air quality monitoring and self-evaluation. Thank you. And now is the moment of Dr. Zinzi. I will give him the presenter role, and that's it. Michele, up to you.
Thank you, Giacomo, for inviting me to this event, and thanks for the colleagues and the students that are attending. So Giacomo has already introduced my presentation, so I think we can skip this first slide and going directly to the contents of my presentation. That will be the description of the Living Lab we have here in ENEA with its main technological feature. We will have a description of our equipments, and then we will describe one application of our Living Lab that was related to a performance gap study. The Living Lab is located in the Casaccia Research Center of ENEA. We are the National Agency for Energy, Environment and New Technologies, and this research center is in the northern outskirts of Rome, so a Mediterranean climate. The Living Lab is inside the building named F40. The building as a whole is about 1,000 square meters and hosts offices and some laboratories at the ground floor. About 10 years ago, it was decided to install a smart management system mainly to monitoring environmental and safety aspects. While since 2018, it was decided to expand the functionalities of the smart system, including also the energy issue, to make studies related to the electric transformation perspective. We are living in Italy, probably most of the European Union. And we identified two major actions. The one related to the building performance in general was about energy flexibility and sufficiency studies in a building in which we also installed PV plants, so renewable energy generated on site, and electric storage to optimize the load and the energy performance. And on the other side, the implementation in some rooms of the building of a living lab for energy performance and environmental studies. In both applications, the role of smart technologies was one of the core and the major aims of our study. The Living Lab received through the years several fundings, some at national level, mainly in a wide framework program founded by the Ministry of Industry, the former Ministry of Industry, and other funding coming from the European Union, such as the EDICE project founded by the Horizon program, or the Spoke 8 of the NEST project, which is a national project founded by European funds coming from the Next Generation EU program. Up to date, the living lab consists of these 7 rooms installed in the F40 building. 7 rooms, each room is about 17 square meters, so today the living lab is about 100 square meters. All the rooms are practically the same in terms of geometry and size and orientation. All of them are west oriented. In 2024, we will install 4 additional windows, rooms, so we'll have in total 11 rooms, and in practice we will be able to control and monitor all this portion of our building. Concerning the equipment, 4 of the 7 rooms are equipped with advanced dynamic windows. We renovated existing windows in this room, so the new windows are very similar as a geometry and appearance to the old one. But they are made of a high performance glazing system, double glazing and triple glazing system depending on the rooms. One of the 2 sashes of the window, the small one in particular, is motorized. As you can see here, there is a chain that developing can close or open the sash. And we have a Venetian blind integrated into the glazing system, as you can see on the left figure. The opening of the sash, as well as the Venetian blind, so the shading system, can be operated locally or via the Connex system, which is integrated into the management system of the building. Concerning the energy supply, originally the building has for heating and water as an hydraulic system with local fan coil. They were removed in our living lab and were replaced by direct expansion air conditioning units with inverter to be used for heating and cooling. These machines are quite efficient in terms of energy performance, and on each unit a Modbus interface was installed for data communication, so that they can. It was also possible to connect them to the management system. Finally, in each room we have at least multi-sensor, battery powered and so freestanding, communicating with the management system and with the LoRaWAN technologies. And the measurement parameter of this LC sensor are the area temperature and relative humidity, the illuminance, the CO2 concentration, and the presence. We might have, depending on the experiments and the monitoring campaign to carry on, more than a sensor installed in the room to make local environment studies, like the case of personalized comfort system. And now we come to the SBM, which is a Smart Building Energy Management System that allows to monitor and control almost all the energy and environmental parameter in our Living Lab. It is a kind of experimental setup, so it's open and interoperable, so that it's easy to connect sensor and actuators, even if they dialogue with different protocols and systems. And all the process is managed using the Appio cloud system developed by the Appio company, which is able to implement a microservice to support different part of the monitoring and management campaign we need to run according to the specific services and equipment we have to control. And this is a screenshot of the Appio dashboard. You can see that we have several apps. Each of them is dedicated to specific monitoring and controlling tasks, like the PV plant on the roof with a coupled weather station, the indoor environmental monitoring, the energy metering, the lighting system, and the smart windows management. There are several more apps that are not related to the energy performance assessment of the building. And in particular, in the framework of the EDICE project, there was the need to develop specific hardware and software solutions, as the existing management system did not couple with the Connex system. So a specific developed interface was implemented, so that inside the building management system would have been possible to include the Venetian blind system, the Windows automatic motorized system that were not initially managed by the Appio system. We can skip this. And at the end of this hardware and software work, we were able to monitoring all this part of the living room, the living lab as an example. Beside the environmental condition that we can monitor in each room, we are able to, at room level, to read the state of the window, such opening, the blind opening, and even the tilt of the Venetian blinds. As a writing option, we can decide when and how to close or open the window, how close or open the blinds, and also to fix the tilt of the lamella depending on the sun position. And on the dashboard of the smart system, we can visualize all these options, as well as in the log, the reading of the last 3 hours values. Similarly, also for the energy supply system, for the air conditioning units, the management system is able to read all these parameters that are mainly room air temperature, the set point, the state of the air conditioning unit, the mode, if it's summer, winter, ventilation, the velocity of the air circulation, and the direction, and then a number of electrical data, in particular the absorbed power and the accumulated energy, that for our analysis was the main parameter. As a writing option, as a rule we can implement, we have the temperature set point, the on-off state, the mode, and the operation of the air circulation. So we use our Living Lab to make different experiences in the last couple of years. And one of these was related to the energy performance gap, which is basically the difference between the simulated or calculated energy performance of a building and those that are really monitored in practice. The discrepancy between this value can be quite high, especially in new and good performing buildings. This is the reason why there is a trend in Europe to revise current energy certification scheme that are based on a standard condition, moving toward performance based also on a real operation condition. And the reason that can lead to the performance gap are of different nature, that range between the simplified calculation model to the simplification of the modeling itself, as well as the quality and the availability of data. These activities on the performance gap, which is half measuring and half calculation, was made in cooperation with the Polytechnic of di Torino, the Giacomo's group, in the context of the EDICE project that I mentioned before. The method consisted in several steps: analysis of our building, taking into account the input and the output data, and the monitoring of the building itself and of the relevant climatic parameter measured nearby the building. The development of the detailed numerical model, which was later validated and calibrated against the field data. Once the model was validated across a short period, we took the validated model to perform seasonal simulation so that it was possible to check how different input modes affect the final calculated energy performance and the variation with respect to the monitored data. This is a short presentation, so it will deal only with the building free-floating condition, while we made the same analysis also in condition of active cooling and heating. And the key parameter was the air temperature, since previous monitoring showed that for our rooms there was no significant difference between the air temperature and the operative temperature, which is the recommended performance indicator according to the EN standard. But in this case, as you can see in the diagram, the difference between the two values were very close. And in terms of performance indicator, once we fixed the relevant parameters, we took the number of unmet hours according to the standard mentioned here of the European Union. The monitoring was carried out in our Living Lab. This is an extract of the whole monitoring campaign. It's 11 days in the middle of August 21. In this real season, the building was not occupied because of the summer break. So we focus here on the building thermal free-floating condition, and specific rules were implemented. Just as an example, in room 1, there was no opening of the automated sash, but there was operation of the blind according to the solar irradiation level. In the number 2, we have night opening of the windows to provide night ventilation according to a simple hourly schedule. And again, we had an hourly schedule also for the blind activation. In the number 3, there was a control based on physical parameters. For the night ventilation, it was the difference between the indoor and the outdoor temperature, so that it was possible to ventilate the room only when the outside temperature was significantly lower than the indoor one. And while for the solar irradiation, we kept the same rule than we had for room 1. For room 4, as an example, we only studied the impact of the night ventilation without any rule on the solar irradiation. The remaining room of the Living Lab, they had no installed advanced windows, so we have them in a free-floating condition without any shading and without any night ventilation. All the calculation exercise was done by the Polytechnic of Torino, thanks to the PREDICE platform they developed. Probably as a student, you will have a chance to get a description in detail of this platform, so I can skip it here. Just to say that we used the platform to implement the model and made the calibration exercise. Here you can see the results of the calibration exercise. The 3 exemplary room, we have the red line that are the simulated value. The black lines are the calculated value of the air temperature during the 11 days of test. And here we have the main performance comparison data. The difference between the simulated and calculated value, as well as the maximum temperature difference. And here some statistical data. In particular, I would like to focus on the last one. That is the coefficient of variation of the root mean square error. The ASHRAE guideline measurements of energy and demand savings guideline define that for hourly data, this indicator has to be lower than 30%. And as you can see here, our value was always below 3%. So we were quite lower than the standard, so that we could consider quite well satisfactory the calibration exercise. Once we calibrated the model to make the seasonal variation, we need to make some simplification and also some standardization. As an example, for the occupancy on the longer term, we made interview with the occupants, try to understand their typical office hours, so how many workers in each room and what was their typical occupancy pattern. Then we implemented a single strategy for the night ventilation with the windows opening and the solar shading activation. And these are all the variants we considered once we defined the reference data. So different climatic data taken from the Meteornorm database or by the Italian technical standard for building application. The internal gains according, again, to simplified Italian standard or according to EU standard. Different strategies for the ventilation according to schedule instead of physical parameters, or fixed air exchange for night ventilation purposes according to literature. And also strategies for the shading system. Here we have the results according calculating the unmet hours for the thermal comfort. The class C1, according to the standard, is when the indoor temperature exceeds the comfort bands by 2 degrees. The C2 class, that is typical for offices and for houses, is 3 degrees. And then we introduced C0. That is the unmet hours when our value exceeds only 1 degree band. Here you can find the reference case. We have 400 hours of unmet hours for class 0 and very few hours for C1. So basically the building was in a comfort condition. But then you can observe here that according to the different input mode, we can have quite different results. Just to make an example, because we are running late with the time. In the reference case, if I take the Meteornorm data, the results are very similar. But this is quite suspicious, but this is not satisfactory because Meteornorm data are taken from Rome and are from Fiumicino Airport and not from the city of Rome. And also are referring to standardized data and not specific of a year. So here the similar results it's really as a casualty, I would say. While if you include in the calculation the standard data we have in Italy, you can see that the results are quite impressive. The C1 class, which is counted for very few hours in the reference case, is counted for 700 hours if we use the standard data. And such variation can be observed in several cases depending on the input mode. So coming to the quick conclusion of this short overview, we can say that smart technologies coupled to advanced and efficient building technologies play a relevant role in reducing the energy use and ensure the environmental condition for a user, which is crucial for user-centric perspective, and also help the fruitful integration of renewable energy. Smart technologies can be basically applied to almost all building components and energy services. And a critical issue that still remains today, that many of these smart technologies often travel according to different protocol and system. And this often required an effort of integration. Concerning the study on the performance gap, it proved the crucial role of providing consistent and reliable data coming from monitoring. This is because the monitoring provides information that are specific of the period that we are monitoring and the condition we have in the building. All these specific issues are often neglected on a current energy power certification scheme, which is based on a reference and standardized condition. And this is probably something that will be needed to address with the new directive of energy performance of building that is ready for public. Thanks for your attention, and if you need more information and detail, these are my contacts. Thanks a lot.
Thanks, Michele, thanks a lot. I don't know if you have one or two questions. Otherwise, we continue, we check for eventual elements after. Okay, now we have the presentation by Tristan de Kerchove, ESTIA.
Hi, everyone. Thank you for coming, and thank you, Giacomo, for inviting me. So I'll talk about the challenge for monitoring of and control of a high energy performance building, specifically the case study of PRELUDE here in Switzerland, Geneva. So we selected a building that was newly refurbished in 2021, and this building was added with 2 floors. So they built 2 new floors with a specific floor heating, and these new 2 floors were also connected to the PV system that was installed on the roof. And the 7 first floors that were just refurbished were done so with a quite thick insulation. So both parts are what you can call a high energy performance. Also, all the technical installations were refurbished. So there was a new gas boiler, which is quite powerful for a building so well insulated, but it's because it was due to operate also during the work performed on the building. So it had to produce enough heat for a non-insulated building. And there's also a heat pump with a heat exchange on the exhaust air of the ventilation, and that ventilation is demand controlled. So it depends on the humidity of the rooms it ventilates. Finally, as I said earlier, there's a PV system installed on the roof and a battery of 21 kilowatt hours. So it's quite a complex building, and here I'll go a little bit into detail about the heat production because it's quite specific and quite interesting. So in Switzerland, it can be quite cold during the winter, so we're mainly focused on heat production. Here we use heat for both space heating and domestic hot water. Domestic hot water during the whole year, and then space heating for almost half the year. And thanks to the PRELUDE project, we could install a very thorough monitoring of the heat fluxes. We could, as you can see here on the right, so there are the heat fluxes coming from both the gas boiler and the heat pump. And so on the gas boiler that focuses more on the space heating, you can see 3 counters, both the space heating of the east part and west part of the refurbished floors, and then the floor heating of the last 2 floors. And then you can see that the heat pump both produces water for the preheating water tank for domestic hot water, and also can help the gas boiler in producing the heat for space heating. So here the squares in blue with the C and a number are just the heat counters that we have available. What we focused mainly, the whole smartness of the system was to optimize the heat pump, its functioning so that we would reduce as much as possible the gas consumption. There's a slight bonus to this already pretty great heating facility, is that we can, during the summer, we can exchange heat with the floor heating system instead of the ventilation system. So it adds comfort to the last 2 floors of the building, because the heat is retrieved from there, so their temperature actually reduces. So I show you here like 8 heat counters, but there's not only that. Here I'm showing you the whole technical scheme of the heating facility, just to show you how complex it is, but also how many data points we have available. This is really thanks to PRELUDE, and I would like to underline the fact that this is not a standard Swiss technical installation. Here we pushed it so that it was as evolved as possible, with the state-of-the-art technology, and also with the most extensive monitoring as possible. So all the little squares, either green, red, or orange, are data points available through the EVOSP system of the technical guys over there. So what about also the indoor air quality? For the PRELUDE project, we're not only interested in energy performance, but also in comfort for the occupants. So we had to meet some KPIs related to indoor air quality. And there were already several sensors installed before the refurbishment, measuring temperature and CO2, temperature and humidity, these mainly on the 7 first floors. And then we also added on the last 2 floors in all the room, or most of them, temperature and humidity sensors. And then we also installed 11 CO2 sensors in different bedrooms. The only issue we had, and we hadn't taken that into account when designing the project, was the GDPR compliance restrictions. And as the contact with the tenants was pretty tough, we only had one tenant agreeing to share his data. So most of the indoor air quality data that we are retrieving are then anonymized, so that people from the project cannot know where it actually comes from, which makes it quite annoying for the thorough analysis of the system. How do we actually get the data? Because it's great to have monitoring installed, but in PRELUDE we wanted to have a middleware system. So in the building, we have, as I said, more than 100 sensors, and the technical company there stores it for a year on its server on EVOSP. And then Fusix retrieves these data and stores it on its own server so that we don't have a time limit, or at least not until the end of the project. What we do is that we take the data from Fusix, and we can also check if there is any data gap or anything. We can check on the EVOS platform, which has a online graphical user interface, if the data actually is measured or not on site, and therefore if the issue comes from one or the other link through REST API. So this is how we actually process the data. And this is to underline the fact that it's not a direct connection between the building and ourselves, but we go through Fusix because of this middleware aspect. And it's the whole point of PRELUDE. So it allows us to produce these little graphs. What you can have for a standard monitoring in a standard building, I would say in Switzerland, is most of the time you take the bills and you check the heat demand for space heating and domestic hot water, which usually you have together, because you either have gas bills or oil bills or something like that. And then you can maybe compare it to EPC. So here on the right, you see the results for our building. You see that the heat demand for space heating quite well meets the EPC standard, and unfortunately, the domestic hot water needs are quite high. But at least on the space heating part, we can see that there's almost no performance gap, which is already pretty impressive results. And then you can also have, I mean, in some buildings, you can have in the standard monitored environment, maybe temperature measurement, as you can see here. Here you can just see that the comfort is quite well met. I mean, temperature between 22 and 24, it's almost overheating for some people. In our case, we have extensive monitoring, as I showed you, and so we can have many possibilities of analysis, and I just wanted to outline a few of the possibilities that we have here. So first of them, which is quite interesting, is the analysis of the on-off cycles of the gas boiler that you can see here on the top right. Here I just show the number of change of the system. So it means when it turns on, starting from off, it's like one change. And so you can see that in 2022, so the baseline, there was a lot of status change. And then we changed some parameters in the boiler instruction, meaning that it would only produce heat if some threshold was met for the domestic hot water. And then we can see that the trigger, the status changes are way lower. So it means that the gas boiler just turns on and off less than earlier, which is good for its life cycle. Then we can also evaluate the energy fluxes, as you saw that we have so many heat counters. And then you can see that yeah, sorry, it's in French, but the gas boiler, which is chaudière in French, consumes the whole gas and then produces mainly heat for the space heating, which is chauffage in French. And then the heat pump, which is the pack, mainly takes energy both from the auto-produced PV system and also from the imports, and mainly produces heat for the domestic hot water in green. Finally, we can also analyze, thanks to all the counters we have, the COP of the heat pump related to the start temperature from the evaporator, meaning that you can see that the COP reduces with an increase of departure temperature. So if you ask it to do like lower temperature, its COP increases, which is what we expected. We have so many stuff and it's great. Unfortunately, you have to have some drawbacks. So the counterparts of having such great data and such playful stuff to play with is that you have so many data and so many data points that you might have data gaps and that you don't realize them. So it really asks for a lot of maintenance of the monitoring system and a lot of attention as well. Also, the time for analysis is quite long. We're not a university, we're a company. So time really matters when it comes to analysis, and like how much you spend to give an answer to the client really matters. So you have to make it profitable for you. Like you have to choose the right monitoring size so that you don't have too many datas and you just know what you're going to count. Here we just had a research project, so we wanted to have the most possible so that we could choose for a next project. And finally, the fact that we have so many people that intervene in the data flow circuits makes it hard to coordinate. I mean, we had the EVOSP people and the PhysX people to finally have data to us, meaning that if we have data gaps or any issue, we have to coordinate with both of these guys. And finally, we also had to coordinate to intervene on site with the technical people. We think that the predictive maintenance tool that is developed by STAM will pretty much help a lot with that data gaps, because it will raise some warnings. I wanted to talk a little bit about the predictive maintenance. We had last year in November a ventilation breakdown that happened on November 24th, and it took us, it took the technical guys there 13 days to realize. I said us because we should also have seen it on the data, but we're not monitoring like every day. And it took 7 more days after they realized there was a breakdown to actually fix it. What STAM actually developed, and what we're really interested in, is a predictive maintenance tool that takes signal from the different monitoring points and tells you if there might be or not an issue or a breakdown. And then you have to check and tell the system, is it not? And then it learns from it with a machine learning algorithm, and then gets a little bit more precise and can warn you if there's any breakdown. So yeah, we really appreciate this tool, and we can't wait to test it a little bit further. Finally, what are the lessons learned about that Swiss case study? Because I talked a lot. So as I said, we designed a very interesting technical installation system. We can underline that it really matters to have a great and a well-thought technical system if you want to avoid the performance gap. We would also like to underline the fact that the number of data links or bridges that you have might increase the risks of data gaps. Although here working with Fusix is quite smooth, thanks to the fact that we're working on the same project and we all want to share the same goal, but we'll still sow that. And having a good relationship with the users or the tenants is crucial, and informing them as early as possible of the project and their implication, or at least thought implication in the process, can really help to avoid any issue like we had to anonymize everything and then lose crucial information. Finally, as I said, analysis is quite time consuming, and it needs to be anticipated. Sometimes we underestimate it and we get lost. And finally, verification of the monitoring devices crucial, because then you end up with data gaps that are way too long and that you have to fill, and that can occur quite often. And the word of the end is that no performance gap is actually possible in a multifamily building in cold climates, thanks to the whole monitoring system that we installed and the well-thought design of the building. So yeah, it is possible, but as Michele already said it, monitoring is essential. Thanks a lot for your attention.
Thanks a lot. Thanks a lot, Tristan. That's, again, very, very interesting presentation. And now we have Martin Frandsen from Aalborg University. I will give you presenter role.
Thank you, Giacomo, and thank you for the invite for this presentation. I'll take another direction in showing the lessons learned from monitoring in NZEB buildings. In Denmark, we have 2 demo cases in this PRELUDE project. So I'll show you the lessons learned from what I experienced in 2.5 years to try to have this 2-direction communication from and to the building. So the PRELUDE project's first pilot achievement was to establish a 2-direction communication to monitor and to control the building. So as said, lessons learned from this adventure and some advices for future measurement campaigns that you can have and that I also will use myself. What we need to be clear on in the start is that you have monitoring and you have logging. Monitoring helps you to manage the application performance. So to live see what is the performance of this HVAC system or whatever whatever you have. While logging is about managing this data and put it inside some logs so you have the historical data. The PRELUDE project goal is to be proactive. So we want to take action into account what happens in the future instead of reacting on what happens right now. So the modern control systems are reactive. They react if it's too cold in the building, then we open off the valve for the heating to flow. Or if it's too hot, then we start to ventilate more. The proactive system take into account the historical data. That means that we know how our building is reacting according to outdoor conditions. We know how fast the heating system is acting and how fast the ventilation system is acting. We need historical data for that. And then we also need future predictions. So we need to know what will the weather condition, for instance, be for the next couple of days. Thus, that means that data logging is essential, but is rarely available. So from that as a starter, the agenda for what I'll talk about is what is this PRELUDE two-direction communication and why do we have it. Then a short presentation of the two demo cases. I'm sitting in Aalborg, here in the northern part of Denmark. Then we have Rye as a demo case in the middle part, and then in the south part we have Egernsund. I'll go in detail about the Rye demo case. I actually hope to have time to go into both, but I think the most important part is lessons learned and then the advice for future measurement campaigns. Good. The PRELUDE two-direction communications is about, we have all these technologies in the PRELUDE. We have the free-running module, which POLITO developed. We have weather forecast. We have data predictive control. So technologies that can predict or that can make some control schedules for our buildings. That is communicated to the PRELUDE middleware for CX, which is a middleware where we collect the data, we collect the technologies, and then we are sending control schedules to the building or analyzing the buildings. This is connected to the building's control system. So the physics is the brain of PRELUDE, as I would say it. And then you have the control system is the brain of the building. It's what's control the underfloor heating or radiator, with what's controlling the lighting, the air handling unit, and stuff like that. It also collects the indoor environment, send it to the control system, and then the system is sending the data to the physics platform. That could also be handled by API, for instance. So the two direction is because we need to send data to FOSCX, and then the models need to make these control schedules for the next day or the day after that, and send it back to the control system to act on this. The two buildings in Denmark, we have Rye, which is a single family house. It's one floor. The family living there is a young couple with two toddlers. It's 160 square meters in heating area. And then the ownership, which is quite important, is the tenants. And when I say it's important, it's because when the tenants own a building, then they are also highly motivated to be in the project and to give us the detailed interaction that we actually need to make good analysis and good monitoring. The case in Egernsund is also single-family houses. It has 2 floors and is partly occupied, unoccupied. The floor area is 180 square meters in heated area, and then the ownership is a company which is using this building as a demo case. So the case here is more a living lab demonstration house to show new developed technologies. So it's a bit more rare to have people living in such spaces if everything is not working or is being tested. So that also means that the interaction with the tenants, because they rent into this house, is sometimes more negligible or small. I will only focus on Rue because it's the most simple case of these high-tech solutions. I think the data points and the technology are the double in Egernsson compared to Rue. Yes. So this is just some pictures of the house. If we look at the floor plan Rue, there are 11 rooms where the kitchen dining area and the living room are the occupied or first priority occupied spaces. These are rooms where the tenants are most of the time. If we look at the overview of measured data points, we have 107 data points going from indoor environment to for all of the rooms to the ventilation, the total airflows and air temperatures and stuff like that, the energy used to heating, and the activation in the heating for the underfloor zone, so we know when are heating supplying and when are heating not supplying for each zone in the building. Then the electricity use or energy use is divided in 11 appliance group. That could be lighting, car charging, when the ovens are turned on and stuff like that. Make it more easier to figure out what is the energy or the electricity actually used for. The PV system also monitored, and the same with the cold and hot water energy use. And then we have the control system, which is monitoring or logging the activation automatic if the system is controlling the solar shading or skylights, or the manual activation if the tenants are opening the skylight or closing the skylight, for instance. And then we have some weather parameters. A few pictures. I'll not go much in detail. You have the electrical boards of this in this technical room for this single-family house. I think there are double or maybe triple of necessary devices compared to a normal family house. So in this row, it's all about controlling lighting and solar shading and stuff like this. Below here, we have the brain of the house. Control brain is the PLC, which is a programmable logic control. And then we have the server, which is connected to the FASHEX. So here's where we store all the data. And then we have a laptop, so I can remote access it from Aalborg instead of going to the house all the time. The air handling unit, and then the heating, water, energy metering, and valves and stuff like this. I wrote here that this is way more advanced and extensive than ordinary single-family houses. And then I wrote 3 square meters of technical rooms. It don't sound like much, but for a single-family house, it's a lot of space for using for technical equipment. Yes. So the first lesson learned is location of these IEQ sensors. As you can see from the floor plan and these dots, which are the sensors, they are all placed on internal walls. The sensors in this house measure air temperature, and the tenants has all the internal doors open. That means that the air is moving from room to room, and we get a more or less stable condition, or when we monitor, we think we have a stable condition in the room because the air is flowing from one room to another and they influence each other. So if you try to imagine you have a cold day, you are sitting here in this red highlighted area in the living room. You have 2 glass or 2 windows, big windows actually in this room. If you're sitting here, you will feel cold if it's on a really cold day. The operative temperature will be maybe 2 degrees lower than you measure on the internal wall. This has a quite high impact on the experience temperature, also the analyzed temperature for the tenants. And then it's also have a high influence on the control system performance, because these sensors are connected to the heating system. For instance, if it measures 2 degrees higher than you have where you're actually sitting, then it feels cold here, but the system is not reacting. That's why the first lesson is to think about where you place your sensors, and if it's used for heating, place them on external walls. Otherwise, you'll have more or less the same temperature in the room, or in the house, sorry. The lesson 2 learned is when you do this monitoring campaign, it's really important to identify if there are sensors and energy meters installed. They can all measure it, but can they transfer data? Do they have communication modules in the sensors and the meters that is connected to a monitoring solution? Sometimes you have indoor sensors, but they are not communicating the data, they are only showing the data. If so, you have monitoring solutions, then think that they, for single family houses, often only diagnose the performance. But can they log the data? Because the data you log is the most important thing if you want to be proactive, if you want to analyze this environment you have in the house. And then I also think that Tristan mentioned it. So if you have these systems, it takes really much time to connect it together, to understand how it's working and get the data from it. So it takes more time than you could imagine. If you're implementing new sensors, then I will recommend using API if possible. However, you should be aware that the companies are now knowing that using API becomes a business model, so they start to charge you for getting this data. So then you can think about, should I pay a monthly subscription in my single family house to have some proactive systems, to maybe save some small amounts of energy. Good. Stuff about the established communication. So how do we get the data from the house into the Fusix platform, and the other way around with the schedules? The technology talks with the Fusix platform. Then we have the server in the house, which is used as a way to store schedules sending from the Fusix to the PLC, so this brain of the house, and it's also logging the data from the PLC into the server, so Fusix can connect to that one. So this is the way we connect to Fusix. The PLC is an industrial PMS solution, because that's the only way we can use schedule control. It's the only way we can log data. I have this IHC, that's a smart control in Denmark, used in Denmark, a smart home control. It cannot log data. It can only monitor and control underfloor heating. And it can only do it by one set point. It cannot even make a schedule for 1 week. So we need to have something else to oversteer and sending signal to this system. Yes, and I'll not go in detail, but implementing a server like this into a house requires some knowledge about passing through some firewalls, selecting the correct ports in this communication outside through the internet, and stuff that is called GDPR also need to be established and correct. Some lessons learned from this. It's smart home. It's not smart for data logging and smart control, not always. Now written here that older smart homes are not ready for data logging and limited in remote control. I'll say, and it's also mentioned in the end here, that the novel smart home system it is not so much better. Now you maybe have an application on your mobile phone, but you don't have, like, you can send schedule control or something like that, and you can data log or get access to this logging. So we had a system that did not log historical data and only used for live control and monitoring. And if we want to change some set points in the room, we need to have remote access through a laptop, because the software for controlling this need to be in the house on the same IP address of the internet. Yes, and then we needed an industrial solution. So you need more than just what is normal in single family houses to actually get this data. And the question in the end here is, why should the company invest more on this when they are making systems, smart home systems for people in smaller villages? There's no reason for them. There's no business case for them to do this. Yes, then when you start a measurement campaign, it might lesson 4. It seems stupid to mention, but when you visit the demo site, have a look at all system components and take a lot of pictures. Where the products and the components located, what are the model names, how are they connected together, so just pictures of wires, because you will always be missing pictures when you want to analyze and understand the system. I have 216 pictures from RY, and I'm still sitting and missing some details sometimes. In Egernsson, I have 600 pictures and still missing details. So, yes, take a lot of pictures so you can remember. Then when you come home, sit down, understand your system in detail. What are the settings? What are the configuration and the control possibilities? Because high-tech building have smart solution, but they are not smart if used wrong. So you need to actually know what are the right settings to get this. For instance, in RY, we found a not balanced ventilation system, and we found that the air handling units were not connected to the PLC. It was just running on step 2 all the time, whereas the PLC can go in step 1, 2, and 3 when it's necessary. Then after installation, installing this monitoring system, you start to log the data. And then again, you check, you look at your log data, you create time series and see if the system are reacting as you if you wanted to do. You will identify some problems, and then you need to figure out why they are there. We found out that the solar shaking activation was not locked, and we had what we thought a high imbalance in ventilation system, but that was due to a faulty flow sensors. So you can be misled if you're not checking these things. When problems are fixed, enjoy the monitoring, but always keep an eye on these time series, because problem will occur in the process. Then at the end, I have some advice for future measurement campaigns. You should never trust digital signals before you have checked that the physical system actually is reacting as intended. Sometimes you log and you can see a digital signal, but it's not going through the component. So always check this. And when it comes to research and development, companies promise more than they can keep sometimes. So it's important to know who did you communicate with. Was this a salesperson, what is a leader, or what is a developer in this company? And I try to highlight with colors which you should trust the most. They are sitting with the product. Research is only first priority for you. The craftsmen and technician have the packed working schedule, and they sometimes see research as a playground. I would call it work, but some say it's a playground. So if you want something to go through fast, then you might need to over-dramatize your necessities, meaning that it's about life, death and life, but about this project needs to be finished and we need to have the data. It's really important, or we will throw away a 5-year project, for instance. Yes, then continually reaching out to the companies. It's not fun because you are annoying people, but it's a way of speeding up this installation process. A slide more about this is that when you have already constructed high-tech buildings with novel technology, then it is much more resource demanding to understand what happens in the building and how it's working, that you can actually anticipate. Therefore, building commission is also really highly recommended, because this type of building is very often system where it's not working as intended. That could be a wrong cabling, that could be missing control, or you don't have a balancing of the air handling unit or the ventilation system. And that is leading to high energy use. Then sometimes you can have the thing that replacement can be better than trying to fix stuff. For instance, in Egerton, we have some room thermostat that was not working. We could not get the data. We tried for 1.5 years with this company to make it work. And in the end, we threw it away and said, we don't want to work with this anymore, and changed to another system. It took us a month to get the data, and it was all working. So sometimes there could be less trouble and less cost in just replacing. Then another challenge is overlapping expertise. We have building physics, we have data scientists, software engineers, control specialists, and craftsmen in the projects. And we all have a different background and a different view on data. I think, Tristan, you also mentioned it. And therefore, we see different possibilities and different solutions. So there's a lot of communication going to understand each other. Last slide from my side is about data. You need to ask yourself, who owns the data? Maybe it's the owner of the building, yes, but unfortunately it's not always that simple. The company that has this product not always want to give you the data, even though that the building owner has said it's okay, because they need to have the contract, they need to have the GDPR, NDRs, and things like this on the place to give the data. Then is historical data available? Maybe you have, and that is good. Then you need to look into how does it look like. It is continuous. Do you have gap? What about the quality resolution? It matters if you have it in megawatt hours or in kilowatt hours. That can be something that you can analyze more detail if you have it in a higher resolution. And the last thing, something called GDPR, NDR, and data access from third-party technology providers is a good thing to have, but it also stresses this issues of getting the data and work with it. That was all from my side. Hope you can use some of it, or otherwise I hope that, Giacomo, that you will share the presentation for use in the future.
Thanks a lot, Martin. That's very interesting, at least for me. I look a lot of the issue that you mentioned and lesson learned is exactly what we touch, no? When we try to make smart, or at least to connect data to what we are thinking now that smart building do, but in reality it's not exactly like that. So it's really, really precious, at least for me. I hope also for the audience. Do you have immediate question? Otherwise, we will try to have someone at the end, and we move to the next presentation.
So, yeah, well, good afternoon to everybody. I'm Enrico Prataviera from the University of Padua, and for this presentation, we are changing topic a little bit because we are moving from real case scenarios where you have monitored buildings to some simulation-based analysis. And my presentation is divided into two parts, basically, because first of all, I would like to explain and go more into detail into the the concept of energy flexibility in buildings and how you can actually exploit it and why you need to exploit it in the control of a building. And then in the second part, we are gonna speak about the activity itself that we carried out inside the PRELUDE project. So you have here two definitions that are in the context of energy flexibility of a building. But just to summarize them all, let's say, the energy flexibility of a building is actually the ability that you have to change and shift the energy consumption that you have inside the building in time. So during a day, for example, you might want to generate or use the energy in a different moment and in a decoupled moment compared to the consumption itself. So basically, inside a building, we have some sources of flexibility that can help us in doing such. But why do we need flexibility inside a building? So you have many issues in nowadays buildings, especially in new NZEB buildings, for example, where a lot of electrical devices are actually installed. But we can see some of them here. So first of all, the price of electricity. The price of electricity is not constant all over the day. You might know that inside your bills you have some time slots where you have a different price for each time slot. For example, in nighttime, the electricity price is less, so you might want to use the electricity energy during nighttime, and you can do that, for example, with a washing machine. But also, from the point of view of the operator, the energy flexibility of a building can be used to keep the electric grid stable, because if 100,000 buildings actually turns on the washing machine at the same time, this is a very big problem for the electricity operator. Maybe you know that, but let's say, very drastic change in the electric load for the grid are a problem. And the flexibility of buildings can help the grid operator in managing them. And third problem is renewables, which are, of course, you cannot plan the generation of electricity or energy in general with renewables, and you need some kind of control of them. This applies especially to the electric grid and the electric energy that you consume in a building, but it can be applied also to some other vectors like, for example, district heating or cooling. By the way, as I told you, you can use the appliances to shift the electric load during nighttime, for example, with a washing machine, but there are some other sources that you can use inside a building. And the major sources that you can use also in automatic control of a building are storages. So probably all of you know that the storages that you can have inside a building can be electric batteries or maybe water tanks. Let's focus just a moment in electric batteries. You have, for example, you might have the production from a solar PV field, okay, and you know that that production is concentrated during daytime, especially during the central hour of the day. But you need to store that energy inside an electric battery to then use it afterwards. And these are just a couple of data on what are the typical electricity, the energy that you can actually install inside a building. This is a typical size from 2 to 15 kilowatt hours for a house. But then you might have also thermal storages like water tanks. Increasing the temperature of a water tank actually is kind of storing the energy, the thermal energy inside that tank. And you have another example. Of course, water tanks are basically the oldest energy storages that you have in buildings, because they have been almost from the beginning applied to the heating systems. Okay. By the way, there is a third storage that you can actually exploit inside a building, which is the building itself. The building, like walls, floors, ceilings, and the structures, okay, are a storage that you can heat up or cool down using some automatic and, let's say, smart logic. And this can help. For example, you have an example on the right side of the slide here. This is a taps system. You might know it's similar to a standard radiant floor, okay? But the pipes in this case are inside of the slab. So usually in your house, the pipe of the radiant floor are very close to the tiles or maybe your pavement, okay? In this case, the pipes of hot or cool water are inside the slab, and this is used to actually heat up or cool down the structure of the building during nighttime, for example. And this is used especially in commercial buildings, like also offices, in cooling season. So you cool down the building during nighttime because the efficiency of the system is higher, and then you use this cool building when the load is high, like during daytime, with the solar addition and all the internal heat gains. And this is an example of what happens. So you can see here on the left side two cases. The blue case is the standard one. This is for a standard heating set point. You have the blue line that goes up at 6 a.m. Okay. And the temperature goes from 18 to 21 in this case, and this is basically the energy that is consumed inside this case, okay. But you can, of course, anticipate a little bit the turn on of the system, which is the red case. And in this case, you're gonna basically consume slightly more, okay. Because of course there are some inefficiency of doing so, but you can reach a temperature that is more comfortable before. And the same you can do for the turn off of the system. So you can anticipate, you can just delay of a few hours the turn off of the system. And in this case, you can see that the temperature follows a profile that is different from the standard blue case. And at this point, you will have a higher temperature, which helps also the turn on. Of course, the price of this is more energy that is consumed. But yeah, okay. Before moving to the activity, I would like just to introduce the concept of the discomfort. I don't know if this is something familiar to you, but basically the comfort inside an ambient, inside a room like this, is not just the matter of the air temperature, but is a matter also of the surface's temperature that you have around you. So basically, in our analysis, we use the operative temperature as a discomfort index calculated with this standard, okay, with the procedure inside this standard. And there should be a formula here, but for some reason it disappeared. But basically, what I would like to explain you is just that the discomfort index that we calculated in this analysis was basically the integral between the reference temperature, so the comfort temperature, and the real temperature of operative temperature of the ambient. But yeah, no worries. So going to the activity, what we did was basically a parametric analysis of the turning on schedule of the heating system with this case study building from the PRELUDE project. Yeah, nothing very crazy. It's flat here in Turin. And what we did basically was to change the heating schedule inside the simulation of energy class to just see if there was some kind of, let's say, strategy that we could apply that actually improves the comfort or maybe improves the energy consumption with this specific case study, which has also, this is something that I forgot to tell you before, but which has radiators as heating systems. So what we changed was basically the set point temperature from 19 to 23 degrees, the setback temperature, so the temperature when the system is basically off, a ramp parameter that is the time slot from this when the system, let's say, the time slot that is used to change from the setback to the set point, but we will see later, and then a delay. So basically shifting later and before the schedule. We also changed the radiative heat fraction of the radiators, but this is something that I'm not focusing on it in this presentation, but just to explain you better, you have the setback temperature, the set point temperature, the ramp, so in how much time the change is done, and then the delay. And all these combinations are actually run using Energy Plus. The results that we okay, also here there are some formulas that disappeared, but the results that we actually considered for this presentation, for this activity, are the energy that has been consumed by the radiators, so not the consumed energy from the boiler, okay, just the one that was released by the radiators inside the room. The comfort index, as I told you before, and then the last one is about the peak, so the heating demand peak, because this is interesting, because with some changes in the heating set point schedule, we can also reduce the peak, and this is important also for the design of the heating system. Okay, yeah, they were pretty easy formulas, and just to explain the concept. The parametric analysis is very simple to understand. We ran a lot of simulations, and we just took the results in a big table with all the results of the three parameters that I mentioned. So, of course, we can have different kind of results. For example, you can see for, the first slide is about a more comfort-driven scenario, where we have a ramp of 40 minutes and a delay of 30 minutes, where we have an increase of 5% on the energy that is consumed and delivered by the radiators, and then a discomfort reduction, so positive, okay, so a more comfort of about 22%. Of course, we can have a more consumption-driven case where we can reduce the energy consumption about 3%, but with a discomfort increasing of about 10%. So the first lesson is that comfort and consumption are a trade-off, and it is basically impossible to reduce both discomfort and energy consumption. But what you can do is actually, as you can see in this slide, with a more intelligent and soft, let's say, turn on of the system, you can actually improve this discomfort slightly. So the blue line is the standard case. Maybe I can just point it. The blue line is the standard case. Once the system is on, the line goes up. This is the operative temperature. But if you preheat a little bit the building, you can still keep the energy almost unchanged, but with a higher comfort at the beginning of the occupied period, that is the one starting from that. So this is a more extended table with some cases where you have basically an energy that is not changed at all, where the discomfort is always actually reduced a little bit because there is a preheating. But also you have a reduction in the peak, the heat demand peak that you have at when the system is turned on. So basically, this helps also in the design of the generation system. If you have a heat pump, reducing the size of the heat pump can actually save you money because it costs less. So, just a couple of conclusions, but we already spoke about them. Comfort and energy consumption are a trade-off, so there is no magical solution. But if you have, and if you apply a more intelligent, let's say, schedule of the heating system, you can have very slight comfort increases, but also reduction in the peak heating demand that you might have, reducing also the design of the systems. And this is done basically preheating a little bit the system with a ramp schedule rather than something that is more stepwise. And yeah, that's it. Thank you. Giacomo, if you want to come. Maybe if they have some question, we can speak later.
Yes, thank you. Thank you very much. Interesting presentation again. I think also very useful to have an idea really how scheduling control and set point control may impact. With very few changes in reality may have quite evident variation. So I think that now we have the last presentation, okay? So I leave directly the floor to Peter Klanatsky from the Forschungsbörgerland.
So good afternoon, everyone. Thank you for the introduction, Giacomo, and thank you for giving us the opportunity to present our results here in this lecture. The topic of my presentation is the long-term test results of data-driven predictive control. So before I start my presentation, Giacomo, can you give me a feedback that you see my presentation, also that you can hear me?
Yes.
Okay. Okay. Thank you. Thank you for the feedback. Okay. So the preparation will include following topics. At first, I will give you a short overview what is a data-driven predictive control approach and why do we need them. After that, I will give you information about the chosen building, which we have considered during the long-term test or in the long-term test. And after that, I will give information how the data-driven predictive control approach works. And the last but not least, I will go into details to present the energy saving potential of the data-driven predictive control solution during the long-term test. So data-driven predictive control, what is this? DPC is a modern control technique, and this technique can use to predict the future behavior of a controlled system. And therefore, you have to define a finite time horizon, and you will get a optimal control inputs which you can use in the controlled system. The DPC requires measurement data from the control system and does not require explicit model knowledge. It makes it more simple than traditional model predictive control. And the DPC is an attractive alternative because we have heard something from Martin. As we become more data in future from the buildings, hopefully it isn't only a monitoring, so we need also logged data information from the building. As you know, the EU reference scenario 2020 predicts that the electricity generation through wind and solar energy will increase until 2050 up to 1,950 terawatt hours. This indicates a significant shift towards renewable energy sources in the coming years. As you know, wind and solar energy are dependent on weather conditions and are therefore intermittent sources of energy, which could require load shifting during periods of energy production. The DPC is suitable for peak shaving and load shifting. With the DPC approach, you are able to optimize the runtime and turn-off time, especially for heat pumps. You can also avoid active heating and cooling during the transitional period, and maybe you can also make an optimization of the full load hours and plant sizing. And with the DPC, you have better exploitation of solar gains. Which building we have chosen for the long-term test? You see on the right side of this slide a photo of the chosen living laboratory Energeticum. It's located in Binkerfeld in Austria. This building is the office building of the Forschung and has approximately 600 square meters usable area. Which are the important technical building equipment? We have an air conditioning system to ensure hygienic air exchange rates in the zones. We also have a gas boiler and heat pump. This heat pump is reversible, so we can use it for cooling or heating purposes. We have a cold water storage tank. We have a hot water storage tank. We have a triple glazing facade. Therefore, we need also shading devices. So we have on the outside external shading devices, Venetian blinds, and also in the inside the building internal shading devices, roller blinds, for example. We have 3 different static cooling or heating surfaces. Therefore, one possibility is the underfloor heating or cooling system. We have also a near surface system in the ceiling and also a concrete core activation in the ceiling. And as you can see, we also have a PV system on the roof of the building. On this slide, you see the ground floor of our chosen building. So the ground floor is one thermal zone. So you see the red dashed dot line. All rooms inside of this area is one thermal zone. So we have only the possibility to switch on the heating or cooling system, and therefore all rooms will be heat up or cool down. On the first floor of the building, we have different offices, and as you can see, each office is more simple a thermal zone. So in some, we have 6 thermal zones on the first floor of the building. In total, we have 7 thermal zones, and we have all 7 thermal zones considered in our long-term test. How works a data-driven predictive control approach? For example, if we put a sensor in a zone and we install a logging of the data information of the sensor, we get the, for example, the room air temperature of the past. If we use a lot of other sensors, we get also other information of the past. For example, you see here on this slide also the heating power, which is used to heat up the room. With the data-driven predictive control approach, we want to build up the future behavior of the zone for a finite time horizon, and therefore the data-driven predictive control approach will consider different control variables. You see in this slide, the forecast horizon is, for example, 10 time steps, yeah? And also the control horizon is only 4 time steps. Yeah? But if we switched on the heating power in this room for the next 4 time steps, we will increasing of the room air temperature, and you see that with the 3rd time step, we have a violation of the upper bound of the room air temperature. So the data-driven predictive control approach don't have a set value of the room air temperature. The DPC algorithm consider the thermal comfort range, for example, from 22 to 25 degrees Celsius. And because of this violation of the room air temperature, the solution for the control variable of the heating power for the room isn't valid. So the DPC algorithm will change the control variable, and more or less the reaction of the heating power is of the shown temperature of about the next 10 time steps. So therefore, we don't have a violation of the constraint, of the temperature constraints. But the question is there another solution where we also have ensured the thermal comfort and where we don't need as much power as you see on this slide? And the data-driven predictive control approach needs always an objective. And for these slides, I use the objective that we want to minimize the energy demand for the next 10 time steps, for example. And if we look forward to the optimal solution, that can be in that way that you see that we only need that we need less heating energy to ensure that thermal behavior in the zone for the next 10 time steps. Okay, this is in general how a data-driven predictive control approach will work. Which models do we need for the DPC approach? And you will see in this slide the different models which we have considered. On the one side, we need gray box models to describe the thermal zones in our experiment. So our experiment, as I have shown, has 7 different thermal zones. And for each of these 7 zones, we need a gray box model with different parameters. We also need an enhanced facade model to consider the irradiance through the Venetian blinds and the triple glazing facade. We need also a gray box model for the PV system to make a forecast about the electrical yield of the PV system. And we also need a gray box model for the hot or cold water storage tank. So in our approach, we only consider one tank because we made a difference between summer or winter operation mode. So in the winter operation mode, we consider the hot water storage tank, and in the summer operation mode, we consider the cold water storage tank. What do we need also? We need the historical data information of the living lab environment. We need the forecast of the weather and the internal loads. We need also the electricity purchase price profile and also the feed-in tariff for the PV power. And with all this information, we can use the mixed integer linear programming optimization with the objective function that we want to minimize the energy costs for the next 24 hours, for example. This is the forecast horizon. And we also have constraints. The 2 important constraints are the thermal comfort range, as I have shown it in the principal scheme, and also the temperature range in the hot or cold water storage tank. How will be looks like a gray box model? You see the model structure which we have chosen for our gray box model. This structure considers 3 resistances and also 3 capacitances. And more or less, you see our state variables. So we have 3 state variables in our gray box model of one thermal zone. We have a direct and indirect measured values. And we also have the model parameters shown in blue color. As you can see, we have 7 parameters, and these 7 parameters are used for one thermal zone. So because we have 7 thermal zones, we in total we have to identify with the historical data information of 49 parameters for all thermal zones. How does our DPC approach work? As you can see, we have our real environment. There's a difference. We distinguish between summer and winter operation mode. We get the actual values, or also the historical data info, and put them into our DPC approach. We also need for our approach the predicted information about the boundary conditions, so the weather forecast. We need the load prediction of the internal loads, occupancy, for example. We also need the energy production of the PV system, and we need also the energy demand of other devices, like the preheater of the air conditioning system in the winter operation mode, or the cooling unit of, or the energy demand of the cooling unit in the summer operation mode. The objective function is to minimize the energy costs, and the constraints are, as I have shown in the table, the considering of the thermal comfort and also the temperature range in the storage tank. With all this information, we can calculate the matrices and vectors for the solver-based optimization, and more or less, hopefully, we can calculate the most cost-effective operation mode of our system, and we can put the solution to as control inputs to the actors of the building. In this slide, you can see which control inputs we used in the winter operation mode. In the winter operation mode, we get a switching signal of our heat pump. The heat pump is reversible. We can load the hot water storage tank with the heat pump, and the operation schedule which we get is for the next 24 hours, and we consider a time step size of 15 minutes. So we get from the optimization algorithm, we get 96 values for switching on or off our heat pump for the next 24 hours. Every 15 minutes, we get a value. We also get a value for the valves of the floor heating system, for example, and also the power. So we get as information the heating power in each thermal zones, and we can use these inputs to write it to the valves in the real building. And it is also important that our office building has a huge area of triple glazing facade. So it is also possible to use solar loads in the winter month to heat up the room, and therefore to reduce the heating energy demand, which comes from the hot water storage tank, for example. Therefore, we also have control inputs for the Venetian blinds of each thermal zone. In the summer operation mode, the reversible heat pump will also load up, or can load up our cold water storage tank, and we need the near surface cooling system in the building to cool down the rooms. So we also can use the control inputs for the near cooling surfaces, so the cooling power, to cool down the rooms, and we can also reduce the solar loads in the thermal zones by increase the shading height of the Venetian blinds, for example. And if we do that, we have a reduction of the solar loads, and maybe through that we can also reduce the energy demand for cooling. How was our DPC approach implemented in the real building? We have a building automation and control network, and therefore we also have a backnet OPC server, and we used MATLAB with an OPC toolbox, and therefore we can read values from the backnet to the workspace in MATLAB. We can make our calculations and optimization in MATLAB, and the output of the optimization is the control input, which we will write in BACnet. So therefore, we will write to the heat pump that the heat pump should be shut on, and also that the floor heating system in zone A, B, C, and so on have to consider power of the outcome of the optimization algorithm. Because the algorithm, the DPC approach, is an open loop algorithm, we have to consider that the optimization algorithm should be done periodically. So in this figure, you see also that we made the optimization on a hourly basis, and also the parameter identification with the historical data from the building always at midnight, once a day. So the gray box parameter will be identified once a day at midnight. And after showing you in short the building with our DPC approach, with the chosen approach, again go to the results of the DPC control solution during the long-term test. On this figure, you see the cumulative heating energy demand of the building. The continuous blue line is the heating energy demand of the reference year. The reference year is from June 2018 until June 2019. Yeah. The dashed blue line is the heating energy demand of the adjusted baseline. That's the energy demand if we had not taken any measure, for example. And the measured cumulative energy demand during the long-term test is shown in the red line. And as you can see, we have energy savings more than 15,000 kilowatt hours for heating. In the same way, you see the diagram for the cooling energy demand. So you see that the cumulative cooling energy demand of the reference year is shown as blue line, as continuous blue line. You see also the cooling energy demand of the adjusted baseline and the real measured cooling energy demand of the DPC solution during the long-term test. And you can see that the difference between the adjusted baseline and the data-driven predictive control solution during the long-term test is more or less 20,000 kilowatt hours reduction or energy savings. And because of the reduction of heat loads in our building, we also switched off the gas boiler at the beginning of our long-term test. So in the past, we used the gas boiler for heating purposes. And because of the reduction of the heat losses in the past, we also tried to use the heat pump also for heating. And therefore, because we only used the heat pump for heating and cooling, so we only need electrical energy, we don't need any gas. And therefore, we have 100% of gas savings compared to the adjusted baseline, for example. These are more than 4,000 square meters, cubic meters, sorry, and or more than 40,000 kilowatt hours. The total energy demand of the building is shown in this slide. So in the reference year from June 2018 to June 2019, we have a total energy demand of more than 100,000 kilowatt hours. The adjusted baseline shows us a total energy demand of 100,000 kilowatt hours, and the real measured total energy demand is more or less 40,000 kilowatt hours. This table sums up the slides before. You can see that we have a reduction of the heating energy demand of about 35%. We have a reduction of the cooling energy demand of 79%. We have a reduction of total energy consumption of about 60%. And with the reduction of the gas consumption, we get a CO2 emission reduction of 65%. Other results, for example, is the switching signal of the heat pump. For example, you see 5 days of the August in the year 2022, and you see that the heat pump, which is used for cooling of the building, is more or less switched on only if we have an electrical yield of the PV system. In times where we don't have a yield, for example, here or here, you can see on the or in the diagram below that we have lowest costs for the electrical energy. On the other side, it is important that we can ensure that thermal comfort in the building. You see the relative frequency of the room air temperatures. The left column shows the reference year, and the right column shows the long-term test. And you can see that more or less most of the time we are inside the category 1. And the room air quality is also important. So you see also the CO2 concentration in the rooms, in the reference year, once again, left column, and in the during the long-term test, right column. And as you can see, we are also always have CO2 concentrations below 800 ppm. Okay, so I have shown you the most important results of our long-term test with the chosen DPC approach. And I think what is important for the future, the current or the next step is that we have we made the transfer of the DPC approach to the building automation levels in 2 Danish demo cases. Both of them you have seen in the presentation of Martin. So thanks for listening.
Thank you. Thank you very much, Peter. Very, very interesting again. I don't know if now we have a question.
Yes.
We have one question. So thank you for the presentation. Just one small question that I might miss a detail from the last presentation. So is the target of the optimization the energy reduction? So yeah, is the whole optimization about energy consumption reduction, or is there any other kind of optimization based on the price or maybe self-consumption of renewables or anything else? Thanks.
Thank you for the question. So the principle of the DPC algorithm is to define an objective function. So I think you have summed up in total, the objective function can be minimizing of the energy costs. So you have the costs from your energy supply, you have the costs of the feed-in tariff of the PV system, or the electrical yield of the PV system, and so on. Another objective function can be a minimizing of CO2 emissions. Yeah, so you have to need, or you need therefore conversion factors to calculate the CO2 emissions if you use the electrical energy from the grid, or you use the own produced electrical energy from the PV system. Another question or objective function could be the minimizing of the total energy to operate our building. And another objective function could be the maximizing of the self-consumption of the electrical yield of the PV system. So you have to switch the objective from minimizing to maximizing, or you can consider it in another way, that only you want to minimize the energy which will feed into the electrical grid. But all of these objective functions are possible, and in the long-term test, we only consider as objective function the most cost-efficient operation of the heat pump.
Okay, I think I got it. So you can basically optimize many different targets, but yeah, in the end, the one that you apply is about cost.
Exactly. So if you have the conversion factors for the CO2 emissions, so you need it in kilogram per kilowatt hours, for example, for each energy supplier, then you can also make this objective, or you can also consider this objective in the approach. Yes.
Thank you.
You're welcome.
Thank you. I think since we are almost all there, having a question for all, since I think several of the presentation underline one of the issue in the application into demo, to building, and it lists to lesson learn a sort of barriers, we can say, or limitation, things to be faced. So, what do you think? Can you resume all together in some way, no? Which may be the elements that after the experience that you have done in this building would limit, or would the one that companies will need to face in the next 5 years to spread the smart building, no? Or smart building application in a short. And that's one issue, and I have also a second one is, how do you think are the difficulties for the transdisciplinary vision that potentially is there? No? Because it's clear that we need, is there or there is no a challenge also in the merging in between building physics backgrounds and informatics one, or telecommunication ones? What do you think about these 2 points? That's clearly for everyone. Huh? You partially answer.
Yeah. So this is my opinion, of course, but I would say that on the software point of view and on the building physics point of view, we have many models right now in the literature that can actually help in controlling, with let's say, smart logic buildings. We have seen some of them in the last presentation, but we can apply also different approaches. Probably the highest difficulty in concerning this part is more about creating something that is very scalable for many buildings altogether. So all the models can be applied to single buildings with some specific tweaks, but this needs a lot of knowledge from who actually applies them. While if you want to scale up such kind of model predictive control, for example, logic, we need, of course, as researchers, to develop some models that can be applied more easily, some softwares actually that can apply this kind of logics more easily. And that's more about the software. About the IT architecture, unfortunately, I'm not such an expert, so maybe I'll just let someone else speak about it. But yeah, that's my point of view about it.
Thank you. The general question is about what do you think will be, now that you've already listened, you can say, or you can make a list of that, but what would be interesting to resilience in a way which would be the measure barriers for applying what you have tested in a large scale. We all speak about smart building, but if you want to have a true objective for smart building in the next 5 years, which are the measure, we can say, barriers in some way? What do you think after your experience? And that's one aspect. And the second aspect is, inside this barrier is also, or is not, the difficulties in transdisciplinary between building physics and informatics telecommunication integration. So there are 2 worlds, different you can say, backgrounds. What you experience in terms of conferences and speaking with companies and so on. But that's roughly speaking. Yes.
I would say we have a lot of solutions that are available. Peter shows actually a quite good example of what is possible to have these energy savings. But there's also used a lot of effort and a lot of time of getting there. There's no doubt that I think that the greatest barrier is to get the historical data and to get and to use the money on this, because it's quite cost wise to just buy those products and have them implemented. And I think that again, who will pay for that? Is that the tenants, the building owners? Yes, if you have a really big building where you can see a lot of energy savings, yes, of course, you can see the potential. But if you have smaller buildings, then the price are quite high just to get the control, the solution control is quite high. So from my point of view, we can implement it in bigger buildings with either a lot of offices, or we can implement them in multi-story buildings. The one case Tristan was showing also shows some great potential in a building like that. But from my point of view, because I'm working with single family houses, it's a great effort to just get the data so we can actually make those energy savings and good control possibilities.
And on my side, speaking, good example that we want to show around, and so we can emphasize the advantages of such a monitoring and control. But when you look at how much time and how much money was spent there, we need something simpler. And this is, I would say, the biggest struggle is to outline the simplest model that you can implement so that people would still save money and you wouldn't miss something. So that, I would say, is the challenge. And then quite a lot of different communities. Sometimes it takes a lot of time to adapt to the different ones with either your platform or a final solution. So this is also, I would say, a big challenge when you try to implement a solution.
Thank you both. Thanks. I really thank you, all of you, for this very, very interesting speech. So coming back clearly with the next educational event series lecture conference in the springtime. Thanks a lot. Thanks for all of the speaker. Thanks, and see you next time. Thanks.
Thank you, and enjoy the evening.
Bye. Thank you. Have a nice evening.
Thank you for organizing this event. Bye.